Okay, so this is the video assembly file from last time, and really the only reason I'm able to understand it is because I wrote all these comments, and if I hadn't written these comments, I'd probably have to take a while to figure out what it's doing each time. So I decided that I was going to make a compiled language. So here is that same video program in said compiled language, and right away you can notice a few things, like we have preprocessor defines, we have declaring variables before setting them, and then we have functions. And you might notice we have an assembly block here too inside this function. And this function appears to be returning something. So yeah, there's no actual returns in functions. Functions can just set variables. And currently there's no actual stack variable scope. All variables are just global variables at the moment. But there is stacked expression processing. And we'll get to that. But yeah, so essentially what this assembly block does is I want to have a function that I can call to just get a random number, like we did in our video thing where we just called this random instruction. So I wrote this function with an assembly block that just calls that and then writes the value from the A register, because the random instruction put the random number into the A register, and it writes that value from the A register just into this random return global variable. And this @ symbol means essentially treat it as a pointer. So we actually get the address of this variable, and that's what's being put into this assembly block here. Okay, cool. And then we have this interesting set pixel function, and you might notice that the left-hand side of this function is actually these preprocessor defines from above. So what's actually happening here is I'm not setting a variable named regx to x. I'm actually writing x to this address, which, if you remember, was one of the registers from the video card peripheral. So you can just put an address on the left-hand side of a set, and it will just do it normally, the same as if you put a variable name on the left-hand side of the set, like we do down here, for instance. Okay, and next thing you'll see is this begin block. So normally the code would just start executing at the top, but what would actually happen is we'd go through all of these functions, and then we would run all of the code in them, because there's no actual infrastructure in place to kind of jump over functions when we're not actually calling them. So you always want to put your begin block after all of your function defines at the top, and then the begin is where the program will actually start. Well, actually what it will do is when you put the begin block here at the top, there will be a jump to the begin label, and then this begin block just puts a begin label here. All right, next we have a while loop. See that we have a condition here. And then we're calling a function. We're calling the random function. And the output of the random function just goes into this global variable here. And then we're calling setPixel after we set the output of the random function to this variable c, which is used in the setPixel function. And then we have these if statements that essentially do exactly what we had in our assembly file with our two sub resets, but we can do it without a subroutine here. Well, we could do it without a subroutine in the assembly, but it would be cumbersome to do. So yeah, I mean, this is all pretty self-explanatory. You can see that we have if statements with conditions, and then calling functions inside of if statements. I mean, not a very complicated program. Pretty good way to show off the initial features of the compiler. So let's actually compile this and see what it generates. So I will run python-m mlvm.compiler video.mlvc, and then we want the out to be it'll be an assembly file. The compiler just compiles the compiled language, the MLVC language, to an assembly file. So we'll say out is video.mlvs for assembly. And whoops, this file is in my examples / MLVC folder. Okay, let's check out the file that it generated. And it'll look pretty similar to our file from before that we wrote last time. But you'll see that, first of all, we're defining some variables that we actually have in actual program memory here. So the stack is from 0 to 3FF, so then we can start having like actual global variables starting from 400 onwards. So whenever we define a global variable, it kind of just chooses the next available address after the stack, and then that's where that byte will be essentially. And then from before, this is the begin block I was talking about. There's a jump at the beginning of the assembly file that jumps all the way down to this label here where the program actually begins. And then up here, of course, we have all of our subroutines. And you can see that the compiler puts a lot of nice comments that kind of give us an idea what's going on here. And yeah, all of the subroutines have a return at the end. You can see that the instructions from the ASM block in the compiled language here just kind of made it into the label for the random function subroutine label here. And it annotates that these were from an ASM block in the compiler with these comments. And then here's our set pixel, and just doing exactly what you would expect it to be doing, loading this address, reading the A register. So that's reading from the variable X here, and then preparing to set it into the register X with this write instruction to the value of register X, which was just replaced with 6000 from this preprocessor define. So these preprocessors, whenever this register X like appears, it'll just get that token itself will just be replaced by whatever is after the name of the define and before the semicolon. So yeah, pretty similar to C preprocessor defines. And then we can scroll down a bit further and we can see our main loop. So we actually have a label for the beginning of the loop, and then another label for the end of the loop. And actually at the end of the loop, we always jump back up to the beginning of the loop no matter what, because our conditional is actually happening at the top here. And of course, this is a while one loop, so we're just loading a 1 into the A register. And then we're jumping to the end of the loop if not A. So in this case, we'll never be jumping to the end of the loop because A is always 1 at this point. So this J and A instruction never actually runs and brings us to the end of the program here. And then we have our conditionals. So how the conditionals work is pretty similar to how the while loop works. You just have these labels that are put after the end of the conditional, essentially. So this, like the label for this conditional would be put here. It's just called the else label. So it's what we jump to if this condition is false. So we can actually find that. So here's our LMB64. And then we're reading X into register A and comparing the two. And comparing puts a 1 in register C, I believe, if the two values in register A and B are the same. So then we're jumping if not C to the else conditional here. So skipping all of the content inside those conditionals. And you can see that each conditional has its own ID. And those IDs are just determined by like the order that ifs were placed in the file. And actually, one of the paradigms of the compiler itself is that whenever you write a line, of code, you'll be writing lines of assembly at that position, essentially. So there's no actual like backtracking in the assembly. Whenever I write a line of code, I'm writing to the end of the assembly file no matter what, and I'm never changing anything previously in the assembly file. And I kind of chose that in order to simplify a lot of the thought processes for how I was going to make this compiler. And it does make a few things harder. You'll notice that I don't have else statements currently implemented because I couldn't find like a very elegant way to implement else statements yet with that paradigm in mind, with the idea of no backtracking, because an else statement kind of depends on the if above it, and then the if would jump to different things depending on the else below it. So there would usually be some backtracking in the generated assembly there. But anyway, yeah, this is our generated assembly, pretty similar to what we had before, and now we can just assemble that assembly. Let's do that. So this is video.mlvs, and we'll make a video.bin, and there is our bytecode, and then I will run it. Like so. And that took a while to open for some reason, but yep, there's our same file as before. Same sort of behavior. And of course, like, we can edit the code. Like, for instance, if I wanted there to be like a gap in between the Y lines, I can just change this here. Recompile it, reassemble it, and then run it again. And we have these nice rows now. And now take a look at the compiler itself, actually. I think it's probably some of the hardest code I've ever written in my entire life, but it's a bit messy because I tried to keep it as short as possible and tried to keep it all in one Python file, so it's a little bit hard to organize everything. And it'll definitely need like a couple extra passes to make it all like as good as can be. But this is probably some of the greatest code I've ever written. We have syntax errors. Syntax errors will tell you which line in the file that they happened on. We have memory errors if you like allocate too much memory and you run out of program memory. Got all these preprocessor things. I don't know, like, we have like includes. You can include different files. There's a errors. It's all one big state machine. And it's actually a stacked state machine. So whenever a new state is set, you're appending that to the stack and then potentially popping from the stack later. So yeah, this is the entire compiler. For instance, for like evaluating expressions, I have this infix to RPN, and that basically converts any token expression to an RPN expression of the same thing. And then here's our way that we solve those RPN expressions, which obviously is going to have to use like the stack. So we have these push and pull instructions for because sometimes like we only have 3 registers we're actually working with when it comes to like these different instructions. So if I had something like, I don't know, A and B, or like C and D, I would need to evaluate A and B and then somehow store that evaluation somewhere, and then evaluate C and D and store that evaluation somewhere, and then evaluate the result of the left-hand side or the result of the right-hand side here. And since I don't want to just make like an infinite amount of registers, we obviously use the stack for that, since that's kind of what is most elegant when it comes to reverse Polish notation. Like, you use a stack when you're solving reverse Polish notation in general. So when it comes to like when I basically implemented a normal reverse Polish notation solver, but whenever there would be a answer that would be pushed to the stack, like a result of an operation that would end up being pushed to the stack, I did an actual push instruction, and then I pushed a none to the stack, the solver stack, to kind of indicate that a push instruction was done, so that when we're actually getting elements later, if that none is found, when we're trying to pull from the solver stack, we know to pull from the actual machine stack in order to get that element back. Yeah, I mean, yeah, just for basic reverse Polish notation solver, you pop 2 things from the stack, you get your instruction, and then you append that instruction. And then since every single binary instruction that I have always outputs to the C register, I can always assume that the answer will be in the C register. But in some cases, like if an expression is only 1 element long, like in the case of this MLC file, we have this while 1, so the expression obviously would just be a 1, so that would be a load next day instruction, so we'd only be loading that into the A register. So in that case, the output register would be A. And then this function just solves an expression and then returns which register the answer to the expression ends up in, which is obviously useful because I need to solve expressions in a lot of cases, like for any like condition in an if statement or a while, or like any right-hand side of a set block. Common thing that needs to happen. So you might have already guessed that I wasn't fully satisfied with just this video file. So I actually implemented Pong in MLVC, and this actually includes a graphics library, very basic graphics library that I wrote because I wanted to test the include system. And it has all of the registers. It actually has this new register that I added to the video card, which is just a clear register. So when that register is written to, we just fill the screen with whatever color is passed in. So we can take a look at the Pong file. We include that graphics thing, which has different utilities, like drawing a rectangle, for instance. It's just a basic double loop for drawing a rectangle. And it has these 4 input parameters. So you would set these global variables before calling the function, and then these 2 variables here are supposed to be kind of private variables. That's why they have the underscore in front of them. And these are the 2 iterators used internally in the function for these 2 loops. So let's go to the Pong file, and you see that we're initializing a bunch of variables to be used later. And also I have this Gamepad function. So I implemented another peripheral called the Gamepad, which basically just takes like my keyboard, and it takes 8 buttons from the keyboard, and it outputs the state of those buttons as a byte whenever you read from register 0 on this peripheral. So it's left, right, up, down, A, S, Z, and X. And we actually only use left and right in the Pong game. So this function to read from the Gamepad, essentially, I've defined this Gamepad register up here. This is register 0 on the Gamepad peripheral. So just loading that into the D register and then reading it into A, and then loading the pointer to this variable into the D register and then writing A into this variable. So whenever we call this function, we'll get a byte with the button states from my keyboard in this variable here. And then I've defined 2 bit masks up top for the left and right buttons, since we'll be using those. And then some other defines here, like paddle width, paddle height, size of the ball, size of the screen, like where the paddle should sit on the y-axis, all of that stuff. And then I have this exit function that just calls halt in a ASM block here. And here's the begin block, and here's our main game loop. So we call clear the screen, we get data from the Gamepad, and we have some pretty complex operations here. Actually, you can see this is all one expression, so this actually gets solved perfectly fine, as do all, like this expression. This is all one expression as well. And I mean, a lot of this stuff speaks for itself. Just moving the pedal right, moving the pedal left, making sure that it stays on screen, moving the ball based on the ball velocity, bouncing the ball on the sides of the screens, and then here we have like a score whenever you hit the top score increments. And then here's the logic for deciding whether the ball collided with the paddle on its way down or not. And you can see how lenient it is that you can lay out these expressions. You can just kind of type if, and then you can put any number of white space before this opening bracket, and then it'll just work itself out. And then if we lose, the game will just exit. And then here is our calls to the graphics library, where I'm setting all of these input variables that we had in our graphics.mlvc here, and then calling this drawRect function. So I'm drawing the ball, the paddle, the score, and then I'm calling screen flip, which in my graphics thing is just writing a 1 to the flip register. And so yeah, we can run this. So first let's compile it. So let's do compiler, and it's pong.mlvc to pong.mlvs. And that generated a pretty big assembly file. We'll check it out after we check out the game. So let's run the assembler. So here we have the assembler, and we will input pong.mlvs, and then our output is pong.bin. And there is our binary file. It's pretty big. You can see that it's taken lots of bytes actually, and something like 600 bytes or something. And now we can run it. So I will run it without the just-in-time compiler, or else it will go way too fast and I will immediately lose. So let's do python-m MLVM, and then pass in pong.bin. And right away, you can see that we have Pong. And there I lost, and it called halt. Let's run it again. Oops. See at the top, we have our score. Running at about 90 FPS without the just-in-time compiler. With the just-in-time compiler, that really helps this. It runs at something like 600 FPS. And the FPS is counted whenever we actually write to the flip register. Oh yeah, just Pong. So we can take a look at the assembly file here, and you can see that it is quite large. This is not it. Here it is. It is a good 330 lines of assembly here. So let's go to the top. You can see that in our, let's get back up the MLVC file as well. First thing that happened was our include. So actually the first things in this file are the functions from the graphics library here. Those are just kind of directly thrown in at that point in the file. So here's our set pixel. Here's like allocating the variables here. Here's our rectangle function. We got the two while loops here. Pretty interesting stuff. Then here's our main game loop. Here's our main game loop. Here's the one gamepad function. Speaks for itself, basically. Exit function. And then we have our game loop logic here. And the interesting part, I mean, a lot of it is just kind of what you've already seen in the other video file. But you can kind of see some complex expressions being resolved here. You can see these push and pull instructions here. For instance, let's see, what is this one? We're loading 3 into B and 60 into A, and then subtracting. So that's subtracting 60 from 3. So if I go into my pong.mlvc, it looks like the paddle Y is 60 and the ball size is 3. So it's probably actually this condition here. So it looks like the first thing we're solving is the paddle Y minus ball size. So we load the paddle Y, we load the ball size, we subtract, we push that to the stack. We pull, whenever you pull it goes into the C register, we set B to C, and we're loading the ball Y, as shown here, into the A register, doing a comparison, pushing that to the stack. Then, what's next? We're loading 1 into B, then we're loading the ball velocity Y into A, comparing, pushing them to the stack. And we pull both of those from the stack, and we do a logical AND on them. We push the result of the logical AND into the stack. Then we load a 3 into the B register. It's this line, then this line. And then, hopefully at the very end, the result of this massive conditional will be in the C register. So yeah, that is a pretty complex condition, and it is handled beautifully by the reverse Polish notation solver. Though you might have noticed that there is some inefficiencies in it. Sometimes it does things that it doesn't have to. Like earlier, you probably noticed that it pushed the stack and then it immediately pulled back off the stack. Obviously, we don't want to waste instructions like that. We could just use one set instruction and never deal with the stack at all. But it doesn't always do the smartest things every time. I mean, I'd probably need to do some sort of post-processor on the assembly if I wanted to find optimizations like that. But I think it's a pretty good start. There's a lot of things I want to do with this language. I'm fairly happy with how much I did for it in such a short amount of time, and especially with how how much functionality I have in this compiler in just 500 lines of Python. I mean, it's really like very high utility language in such a small amount of code to make it work. I mean, yeah, if you care about any of this stuff, I guess you can read through it as I scroll and pause, but a lot of it's very complex logic that I would have to decipher to figure out how it worked again, and this is all stuff that I'm gonna have to go back and clean up and redocument later, but it works. So, things I want to add in the future, I would like to have, I'd like to use the stack more. Obviously, I don't want everything to be a global variable like it is right now. That's gonna be a namespace problem really quickly, and then it's kind of dumb that you can't have like any local variables and any functions. So, like in the graphics, I had to make these two global variables, which are only used as local variables here. So I'll probably have to like actually make real scoped stack memory and stuff like that. I want to add namespaces, so whenever you include from a file, you don't like instantly pollute your namespace with anything from that file. I think the only things that would be in the global namespace would be these defines. So a few other things. I need to add else's. I'm probably going to add else ifs when I add else's, since it's a fairly trivial addition once you have else's. I mean, else's aren't like a need sort of thing, but they make your life slightly less hell, and I want to implement them in such a way that I'm not like reevaluating a condition if I don't have to. And then aside from that, obviously I want to be able to pass arguments into functions. I don't know if I already said that. And then I want return values from functions to actually be pushed to the stack, probably, instead of be set into some like dedicated variable for them, like we have in this gamepad. Like we have this gamepad return value. Ideally, when I call like gamepad, it pushes its value onto the stack, its return value, and then if I want that return value, I just pull it off of the stack. Anyway, yeah, that is my progress update. I think it is very nice. Maybe even noticed that I even like added syntax highlighting in VS Code for my language to make it a little bit easier to read. But yeah, that is progress update number 2, and hopefully next time I make one of these videos, I will have slightly more functional language and maybe a fully functioning debugger. And if things really go well, I'll be able to have variables that represent more than just a byte, because right now every variable represents a byte. Don't have any halves. Obviously don't have any floats. Everything's a byte, which I had to do some tricky logic to get around that. Like, I had to add like the ball size to the screen height somewhere, because like it would overflow off the left of the screen and then the ball would always fall into the void. But yeah, there you go.